Hello, my name is Maggie Welch, and today I'll be presenting on bat echolocation, and I'll be doing some practice problems as well. The first thing to know are what are the types of calls or pulses. The first one is frequency modulated or FM pulses. These are the ones that start at a high frequency and then decrease suddenly, and they're best in cluttered environments because they're better at computing range. So when you're in a highly cluttered environment, you want a rapidly updating image of what your environment looks like. So that's why when bats are in a highly cluttered environment, they're more likely to use an FM pulse to see their environment. The other type of pulse is constant frequency, frequency modulated, or CF-FM. The CF component is constant, as you can see here, and then the FM component, as we saw earlier, sharply drops off. CF-FM pulses are better in open spaces, and they're better for computing prey velocity. So you can see here in an uncluttered environment, bats are more likely to use the CF-FM pulses than they are to use the FM pulses. There are three phases of prey capture for bats. We have search, approach, and terminal buzz. As a bat is going through these phases of prey capture, their pulse duration will decrease, so their pulses will get closer together until they capture their prey. Bats get quite a lot of information from their calls, so we can ask ourselves some questions in order to determine what kind of information that they receive. The first question we can ask ourselves is, how does a bat detect azimuth position? So azimuth is on the horizontal plane, and they do that like other mammals by using interoral intensity difference and interoral time difference, or IID and ITD. The next question we can ask ourselves is, how does a bat detect elevation of the target? And again, like other mammals, they use notch frequencies in order to determine elevation, which is on the vertical plane. The next question is, how does a bat detect range of the target? For range of the target, the bats use echo delay, so how long it takes for their pulse to return to their ears. Now, how does a bat detect the speed of the target? So we talked earlier about how the constant frequency modulated bats are best at detecting the speed of the target. And that's because they're really good at using or calculating Doppler shift. So Doppler shift says that if echo frequency is increased compared to the call, the bat is gaining on the insect, but if it decreases, the bat is losing the race. So think about if a bat emits 62 hertz and it comes back at 65 hertz, the bat is gaining on the insect, but if it comes back at 60 hertz, then the bat is losing the race. Final question is, how does a bat detect target size? And that is via echo intensity, so how loud the pulse is when it returns to their ears. There are several formulas to know when talking about bat echolocation. The first one is Doppler shift or velocity difference, and this one is useful in determining the speed of the target. So for this one, it's important to note that if the change in velocity is positive, that means the bat is approaching the target, or it's getting closer. And if the change in velocity is negative, that means the bat is losing to the target, so they're losing the race. The duty cycle formula is used to determine the period of overlap of the emitted pulse and the echo of the pulse. Tension change is used to determine how much change in tension you need on the cricothyroid muscle in order to change the frequency emitted by the bat. Time delay is used to determine target range. We have the power ratio, which is used to determine the power difference between the emitted signal and the received echo. We have frequency, which again is just to calculate frequency, and then target range, which is a way of determining echo delay. We are going to be doing practice problems on the Doppler shift velocity difference formula, the tension change formula, and the power ratio formula. So for our first practice problem, we're going to calculate the difference in speeds between a bat and a moth if the bat emitted a call at 60 kilohertz and received its echo at 62 kilohertz. Does the distance shorten or grow? For this, we're going to be using the Doppler shift formula or the change in velocity formula. C is the speed of sound in air, which is 343 meters per second. The change in frequency is 62 minus 60, and obviously these are kilohertz, so we have to do the times 10 to the third. In the denominator, we have 2 times the frequency that it's at, that they emit the signal, which is 60 kilohertz. That's where you have 60 times 10 to the third. If we do this math, we get 5.72 meters per second. Because this is positive, that means that the distance is shortening between the bat and the moth, because if you have a positive value, that means the bat is approaching the target, and if you have a negative value, the bat is losing to the target. So we can say that the distance shortens because the frequency is increasing. This means that the bat is getting closer to the moth and compressing the sound waves, therefore making them a higher frequency. For our second practice problem, we have what is the power ratio in decibels between the emitted signal and the received echo signal if the distance between a bat and a moth is 20 meters. So for this, we're using the power ratio formula, which is 10 log base 10 of P over PO. PO in this case is the surface area of a sphere, which is 4 pi r squared. R would be the distance between the bat and the moth, which is 20 meters. The reason why it's the surface area of a sphere is because when a bat emits its pulse, the sound waves go in every direction all around the bat. They don't just go to the moth itself. So that's why we get the surface area of a sphere in our denominator. And we square this because the sound has to go to the moth and then it has to come back. So this whole thing, the whole denominator is squared. So we get 4 pi squared, and then the r squared is squared, so that's why we get 20 quadrupled. If we do this math, we will get negative 74 decibels. So that is the power ratio between the emitted signal and the received echo. For the last practice problem, we have how much does the tension change from 60 to 50 hertz? So for this, we're using the tension change formula, so you can see that this is a fraction, and we'll just plug in 60 and 50 hertz and cross out the common denominators in order to get 60 divided by 50 equals the tension at 60 hertz over the tension at 50 hertz. So for this, we can divide 60 by 50 and then square both sides to get rid of the square root symbol. So we get 1.2 squared equals the tension at 60 hertz over the tension at 50 hertz. From here, we can multiply both sides by 50 and divide both sides by 1.44, which is 1.2 squared. From that, we get the tension at 50 hertz is equal to the tension at 60 hertz divided by 1.44. So this is how much tension change the bat needs to do to its cricothyroid muscle in order to change its frequency from 60 to 50 hertz. So think about when bats emit a frequency modulated pulse, they need to quickly decrease the tension of their cricothyroid muscle in order to decrease their frequency, right? So they're doing this readily and in order to change the frequency of their pulse.